All right, there you go. Perfect. I'm Arman Amjalar. I live in Berlin. I founded a company called Coyote GmbH, which is a school of software engineering. We also work with various companies with a model called CTO and the team as a service, because if there's anything better than hiring an engineer, it's hiring an entire team with an existing culture. Now, I am very much active in open source, and I wrote a lot of libraries. Some libraries I manually coded, some of them I vibe coded, and this would be the other talk that I would give today that we kind of switched out for AGI. And like I'm gonna make this available later on, this presentation, and if you take a picture and Google the names, I think you're gonna see several libraries. I was able to write a collaboration application because my favorite collaboration application around was shutting down, so I wrote a copy of it with vibe coding. I wrote a layer for Express to have type safety for all of my endpoints and all of the post, get, etc. actions. I wrote a copy of MongoDB query language that allows me to query any PostgreSQL database. I built an in-memory database. I copied Apple's liquid glass thing, UI interaction thing, on the day of their launch, thanks to vibe coding. I also built a game. I revived one of my childhood games from 30 years ago, which was written in Amiga, and I have no idea how that works. So I kind of was able to reverse engineer an entire Amiga tech stack, figure out how the engine works, and build it as an open source game. You can all check them out. So I love vibe coding and I love AI, and I know that we need more intelligent AI agents. And that's something I've been doing with the companies that I work for, OpenServe and Neol. Also feel free to check them out. But we're very big in AI agents. Now, the first question that I want to get started with is, how do humans learn? How did the society evolve? And where does machine learning really come from? Now, raise your hands if you know the actual origins of machine learning. Why did we come up with the idea? Why did we need machine learning in the very first place? Anyone? No? All right. The reason was because we wanted to experiment with human learning. We wanted to come up with systems to let humans learn better, like improve our educational systems. And for that, we needed a model of human learning and reasoning. That's why we built neural networks, basically, to mimic how humans learn, or how the human brain learns, the correlation between different topics. So that we thought, if we have an engine like this, we can run a lot of different simulations for different educational systems. Of course, that didn't really go so well so far. But here's the thing. Artificial general intelligence is not a monumental leap. People were talking about this last year, Sam Altman and so on. They have stopped talking about it nowadays because they now understood that it's not GPT-5 or GPT-6. It's going to come from emergence and emergent properties, and I'm going to talk a little bit about what they mean. Now, the thing is, of course, large language models that we have today are also not artificial general intelligence. They're never going to be able to exhibit those properties on their own. And before we get to that, maybe let's talk about what they really are. They are a complex equation for predicting the next word in a series of words. I'm pretty sure you all know this by now. But yeah, before we go on, let's maybe take a step back and talk about intelligence. There is no universal definition of intelligence. I tried to sum up some of the aspects of what intelligence is, and it's ability to learn, ability to adapt to your environment, ability to use some tools, understanding of your environment, perception, sensors, or abstract away some of the ideas, apply logic, and solve problems. And for these, in order to learn and apply them, or to move your learnings to the next generation, we need memory and stuff. So intelligence is a very complex process. It's everything, all of these systems working in conjunction together. So the question then becomes, can you, or how do you imitate intelligence with next token prediction? Like all of that difficult systems coming together, how do we really replicate that or copy that with next token prediction, which is what we have in large language models today. Now, the question that kicks this off is, how does one catch a ball? I think we tried this at the beginning of the talk. Did anyone not see that part when I tried throwing the ball to some random people? And, oh, sorry. And they were not able to catch it and send it back to me. That's lost, right? The ball is lost. No, all good. All right, perfect. So the question is, how does a person catch, or at least try to catch a ball? How does that work in your brain? It seems very intuitive, right? We also talked about this before the talk. We talked about this and said you don't even need to see it, because when you were throwing the ball back at me, I didn't actually see it because there are these lights over here. So the thing is, it's the combination of many different parts of your brain working together. It's really complicated. You have the visual processing of, like, you need to figure out where the ball is and how it's thrown and understand the velocity and where it's going to be in like 200 or 300 milliseconds time. You need to plan your movement, get into position, and you need to do that movement itself. And when you catch the ball, it might deflect off your hand. So you need to understand the softness of the ball, how much pressure you need to apply, and how tough the ball is in order to be able to grab it and not let it go. So this is the coordination of a very complicated structure in your brain, and it's not a single center. It's actually like 7 different centers of your brain that's collaborating just to catch a ball. And in fact, everyone is living in the past. Like, reality doesn't exist as we know it. Our brains are interpreting it like at least 100, 200 milliseconds later than things happen objectively in real life for everyone, for atomic clocks. So we're even like predicting the future. All of this is happening before we see the ball. And somehow we're able to coordinate. Now, the thing is, it's coming up. Next slide. Great. The thing is, the human brain is a distributed network of multiple centers that are specialized in certain topics. And if that can yield, like those centers working together, can yield general intelligence, can we take example from that, from nature itself, and come up with a similar mechanism to implement artificial general intelligence? This is the question. Can we have a sufficiently advanced multi-agent system to achieve a similar outcome for our goals of having like general intelligence? And here's the thing. This is called emergence. This behavior of like seemingly unrelated things coming together to form a new behavior is called emergent behavior. Now, raise your hands if you're familiar with this term, emergence or emergent behavior. Very good. There are several people already. Now, the idea is this. There are levels of complexity, and each level, somehow, magically, we don't know how or why, each level can exhibit entirely new behaviors. Atoms form molecules. Molecules form cells. Cells form organisms. And organisms exhibit different behavior, like humans can learn, and that there are different animals that do different things. We don't know how the jump happens. Where does it come from? Like, how do atoms suddenly start exhibiting intelligence? How do they become neurons? How do they even replicate in the first place in our cells? We don't know how or where the exact switch is per layer, but we know that with chance, sophistication, somehow, by magic, there are emergent behaviors in these systems. Like, you put a bunch of brain cells together, individually they're neurons. You put them together, they form bonds called synapses, and then, if you tie it to some eyes as sensors or some muscles as motors, they become exhibiting entirely new behaviors. It's crazy. But this is called emergence, and it's what governs the nature, what governs our life, and this can also be applied to humans and societies and cities and countries. We see emergence at multiple layers. So the question is, if emergent properties in nature can lead to consciousness, that's what we're interested in, generic intelligence and reasoning, general ability of intelligence, can we do that with multi-agent systems? Can they come together, and when they do come together, cause these emergent behaviors or outputs to form? Now, what do you see here on the screen? What is this? An arrow? What else? Boxes and circles, yeah. That's basically it. So raise your hands if you see an arrow. Pretty much everyone. Yeah, there are no arrows here. It's an emergent understanding of it. There are boxes and circles with different colors. Like, objectively, that's what it is. But our understanding is that this is an arrow. Why? Because there's meaning in those shapes, right? I mean, it's an arrow, but we fill in the gaps. What do you see here? Pac-Man, very good, very meta. What do you see here? A triangle, right? Except it's in the negative space. So, like, there's no triangle. There are like 3 circles with, I don't know, 60 degrees of gaps. And when you put them in a certain alignment, it looks like there's a triangle. So what I'm trying to get at is that, oh wait, one more. There's actually one more. Ha! The famous shape. What is this? The Holy Grail, yes. The Holy Grail of psychology. What else is this? What do you see here? 2 faces. What else? Candle holder, yeah. What else? It's like a cup, or something like that. That it can chandelier or whatever it's called. But also it's 2 faces. Yeah, this is a very famous picture, or at least like it's an imitation of a very famous picture. Does anyone know the original source of this? Or where this kind of shape is used? What? I'm not sure I understand. Psychology, yes. Therapies. People use this in order to shape out how you think, what you think, how you see the world, how you understand the world, and how you interact with it. So this principle is called Gestalt. And now that we're in Germany, I guess I don't really need to explain this, and we know what it really means. But the sum, or the whole, is greater than the sum of its parts. And that's what we saw in all of these charts, right? The whole actually tells you way more than the sum of its parts. So now, if we apply this principle to AI agents, what we see is individual agents. This also applies to the brain as well. Individual portions or agents that can do a certain thing well can start becoming really big and can start showing you intelligent outputs when you put them together, when you combine them. Now, our job here as developers is to figure out the best configuration of these agents, these individual behaviors, and we hope that it's going to lead to some emergent behavior and some intelligence. And I mean, if you're using Cursor or any other vibe coding tool today, you kind of see this right now. They have a lot of tools. They learn, they grow. Yes, they sometimes drift off, but they're kind of doing what you want them to do with some exceptions sometimes. But anyway, let's get back to technology. What we believe is we're barely scraping the surface of the existing models of GPT-5 or Claude 4.5 Sonnet. We believe that there is so much more hidden performance in these models that we can take out. I'm not talking about like 10%, 20%. I'm talking about 10 times, 20 times more performance we can get out of these models. And this talk is about finding those ways of how to work with these models. The thing is, first, we need to understand what reasoning means. Does anyone know about an approach called chain of thought? Raise your hands if you know chain of thought, or if you ever heard about it. Okay, well, more than half of the room. It's basically when you use ChatGPT, the newer versions, it sometimes shows you thinking, and it's basically like what this technology or this approach that lets these models think by improving your prompts. So they take in your prompt and they generate output to simulate thinking about what you might be asking for and what might they need to do in order to give you the correct answer. But the thing is, it's really not reasoning, because reasoning is a process. And what chain of thought is doing is giving you more words. It's as if you write those words yourself. So if you took the time, and you could actually come up with, another one long page and paste that into ChatGPT, and you would still have the same performance. It's basically writing more text for you, the ones that you didn't write. Now, a very good way to approach it is what I call memory, insights, and habits. Your agent needs to remember things, like everything that happened, everything that's important the user told it to remember. But then there needs to be 2 more layers of abstraction on top. You need to draw some insights from everything that's happening, what you've learned. Because insights give you a deeper understanding of why certain things are happening, like linking 2 different requests or trying to understand why they're happening so that you can change your behavior. And if you get enough feedback from a user about your behavior and that you need to change it, you should change your habits. And by you, I mean your AI agent. So this is an architecture that no one is using right now. But this is where we should possibly go towards, because this is what makes us human and our human behavior and reasoning. When you join a new company and they tell you they use Trello instead of Jira, you change your habits and you start using Trello. But you have the insights of project management, even though the tool is different. You have the memories of your past, of your nightmares of Jira that you stay away from, right? This is what we need to apply. And of course, the last thing that is in your brain is, or that needs to happen in these AI systems, is specialization. There can never be a single agent that can do everything. It's not how the nature works. Nature is working due to an emergent set of abilities of different parts that are specializing in different tasks. That's how our brain works. That's how our AI agents should work. Great. How do we do this, though? For large language models, we have to use English. Now, German is a little bit better in terms of disambiguity or ambiguity. But English is the main language that we work with in these AI agents. And the problem with that is it's obnoxiously ambiguous. Like there's nothing that tells you about the relationship of words that you see. Everything is hidden in the order of words and how some people came to understand or interpret those words. Now, here's a table. I'm not sure if you can read it. Can you read it? It's not bad, right? So, let's have a look at the examples. Coffee cup, shower gel, travel pillow, or winter coat, or history book. English has these pairs of nouns, noun plus noun, right? The problem is there is nothing in that combination that tells how those nouns are related to one another. You have to guess that from the context. Like, you don't know the relationship of, say, shower gel and dog owner. Gel is used in the shower. Dog owner is not used in the dog. That's not at least how you should do it. Does that make sense? There are a lot of different relationships between words. There are a lot of different concepts, but we're not really encoding them anywhere. They're not visible. The meaning is not visible. But you know how large language models work, right? It's next token prediction. How did I get the meaning? Like if there are no tokens that embody the meaning, it becomes really difficult for a large language model to actually understand what these things really, really, truly mean. And this is the biggest problem with large language models today. I don't know, mosquito spray, hand tool, chicken farm. They all have different connotations and different relationships. Now, the academic way of saying this is that there are no morphological markings or differentiators that tell you the difference between these noun plus noun pairs. Now let's compare that to Turkish, which is a agglutinative language which works with suffixes at the end. Those are like functions that modify the meaning of a word. Now, you see the suffixes here, and you see their applications here. And the very good thing is, the same suffix, when applied to a word, changes the meaning of the word in a definitive way. There is no ambiguity. Like, how do you know the relationship between summer house and ashtray? A tray for ashes, a house for summer, or a case for books, a holder for keys. There's nothing there. But in Turkish, there is a specific token that embodies that meaning. And the same for fisherman, milkman, fishmonger, toy shop. How do you know that's a shop that sells toys rather than a shop that you play with? Right? Well, in Turkish, there's a difference. If you add the ç at the end, that clearly says it's a business of toys. Now, this is great because then you can embed these meanings and you can have much simpler, smaller models that can still give you the same level of understanding and semantics. Now then the question becomes, what if English isn't the best language out there to prompt these agents? What if there's another language? And can we actually take example from this, from another human language like Turkish? Korean is also similar. It also works with suffixes. It's called agglutinative language. Can we take example from this, generalize it, and take it to its extreme? Like, what would be a language that takes this to an extreme And would it work better for large language models? Can we actually train a large language model to be smaller, much more effective, and still exhibit the same level of understanding and reasoning? There was a famous article that says, like, if the title of an article is a question, the answer is almost always yes. And this is also applying to this talk, of course. Like, when I'm asking you these questions, of course, there is the answer is yes. There is a better language and a better way of representing reasoning. And I wish the internet would work and give us some, yeah, perfect. Great. Now, I want to show you a system prompt for an agent that you might write that is very, common, or you could find this everywhere. You could write one yourself, and your system prompts also looks like this. This is a system prompt for a product review analysis agent. Think you're Amazon and people are leaving product reviews, but then there are stars, and you gamble, or people gamble with stars. Because sometimes the companies say, if you give us 5 stars, we're going to give you an extra warranty, right? And sometimes the actual stars that a user puts in does not match their review. This is also true in Germany a lot. I don't know if you saw this. I shop on Amazon a lot, and this is what I see all the time. Like, they give it 3 stars, and they say, it works, does its job. They give it 4 stars, and in the comments, they say it's perfect, just like as I expected. And it's very difficult to know when a German person would give 5 stars on Amazon. Like, I still couldn't figure that out. But there are cultural differences. And in Turkish web pages for online shopping, what we see is practically shops delete 1-star reviews automatically. So people give 5 stars and then talk shit about the products. And the web pages also frontline 5-star reviews. That's the only way to warn your fellow citizens. So this agent aims to kind of change the way we interpret these by labeling them. Looks at the review, looks at the stars, and if there's a discrepancy, it labels them as useful, correct, positive, negative, neutral, or ambiguous. But of course, this is not the only system prompt. You see, like, there is a star rating override. There is sarcasm, because people might be sarcastic in their comments, right? And we need to be able to detect that as well. And if you read the previous prompt, there was some numbers there. Like, you assign this number and assign that number. And if you detect sarcasm, assign this number, right? Do you remember what those were? What the numbers were? Maybe? Not really, right? You can be frank with me. I don't remember. I need to go back to the previous slide and see what those numbers were. Here, like, if positives outnumber negatives by 2 to 1, assign positive, assign negative, proceed to rule 2. It's not really straightforward. You increment the score by 1 or decrement it by 1. And of course, that's not all. We need to talk about the format of our expectations. And yes, that's it. So keywords that change sentiment context. It's all over the place. The rules are all over the place. But this is what you experience with English or any other human language, right? It's procedural. Our languages are procedural in programming terms. From top left to bottom right. It's one single wall of text. And it's very difficult to show how a certain line here is connected to a different line in the previous paragraph, right? How do you do that? You do that by writing more words. And then, since those words might mean anything, they have an ambiguous meaning in English, it becomes really confusing for large language models to follow your exact rules. So the problem is there are a lot of possible paths that the agent would need to take in order to calculate the correct outcome. So if you ever experienced a scenario where your agents are not really following your system prompt, it's because of this, because they just don't know how to follow it. Because you give them a linear wall of text, and you expect it to figure out the paths on its own, which is another process. It's not coming up with the next token. How do large language models solve this, though? Do you know the mechanism? It's called attention. Raise your hands if you know attention, or if you heard about attention mechanism. A lot of people did. Very good. Very good. I encourage you to read a little bit more about the fundamentals of large language models and how we came to today. Attention is all you need is the first paper that you need to read. That's kind of what started this revolution. And we practically figured out a way for this machine learning algorithm to pay attention to previous words. And it kind of can calculate, compute how much attention it needs to pay to any of the previous words. But if your context window is really large, it becomes a problem. So attention is your friend because it lets you have realistic conversations with large language models. But it's your enemy because it really doesn't know where to look at when the context window is really, really large. Like, it doesn't even know where you, like, which parts of the paragraphs are you talking about? Or if you're referring to the 10 messages ago or 20 messages ago in your conversation. It doesn't really know. So we, as designers of these systems, need to pay a little bit more attention to attention. This is a big challenge. And the question then becomes, I don't know, have you heard about context window engineering? That's a new term, right? New on the market, because we have these long contexts, but also they're very expensive, and they don't need all the information. So can we dynamically change the context of an AI agent instead of putting in all the messages to manage it a little bit better, to make it a little bit smarter and prevent it from going off route? So the question is the context window too long? Is it too short? Is it too narrowly focused on one single example that you're trying to give, and it misses the actual user request? Or is it misleading? Is it ambiguous? It's very difficult to know. It's very, very difficult to know. So we need to have a better way. And that way is what we call BRAID, bounded reasoning architecture for inference and decisions. This is what I was referring to when I said we're going to be, we're writing a paper that we're going to be releasing. But papers take a long time, so I decided to talk about it instead, because we have some results that we can show you today. But obviously there is meaning in every word here. Bounded reasoning architecture for inference and decisions. If we're able to limit the amount of tokens in a context window, and if we can improve the quality of those tokens, the meaning that is embedded in each token, can we actually come up with better intelligence? And that's basically what we did. So now, I guess you won't be able to see this. Let's see if I can switch my screen. So, yeah, okay. This is a little bit better. So what does this look like? Anyone? It's like a program. It's a flowchart, right? This is the flowchart of the system prompt that I showed you. That was linear. For some reason, I'm not able to zoom in, so you'll have to do with this. But the thing you see here is there are a lot of decision points that branch off, and they point back and forth. So now, I hope this is a little bit clear. You're trying to convert this chart into linear format with English. And you add tons of extra words in order to indicate when should happen what. Only if there was a better way of encoding this. If only there was a better way, there were a better way of encoding this graph. It would be much better. Yeah, mic drop, exactly. And that is what this is. Now, okay, you can read it. What does it look like? Does anyone recognize this? Mermaid, yes. What is mermaid useful for? It literally does this. Yeah, mermaid is a language that we invented to be able to draw those diagrams. Like the diagram that I showed you before was generated as a result of this. Mermaid is not the first language to do this. We had Plant UML to create UML diagrams for software architecture. This is coming from the 80s, basically. If you were writing software like me in the 90s, you'd know that this was all the rage. You drew a lot of architectural diagrams, you communicated with software engineers, and then you implemented those instead of vibe coding. That was the way of vibe coding back then. Like the architect would draw these diagrams and give it to you as an engineer, and you would have to implement those. We were playing the roles of AI. The thing is, this is very clear. Why is it clear? Because Mermaid uses a special token syntax, like dash dash greater than sign, to indicate connections between two different steps. And it's very clear what those steps are doing, the definitions of those steps. So what we're doing here is improving the signal-to-noise ratio of your instructions. There are a lot of signals here. It's very, very easy, especially for a machine, to know that it can go from L1 to G, from L2 to G, and what L2 or L1 are. Instead of dabbling in linear formats, you now have pointers in the system prompt itself. This becomes your system prompt. You give this system prompt to your agent instead of the English version. And of course, this is not the only one. Like there is a second page as well. And do you see the outcomes at the very bottom? S1, S2, S3, S4, S5, sentiments. You see them, right? That's that simple. We say state 1 or sentiment 1 is positive and so on. It's very easy for the AI agent to understand. And the benefit is, obviously, all the large language models today speak this language. They're actually very good at reading, understanding, and executing, or writing, or creating mermaid flowcharts, diagrams. So instead of English as a language to prompt these agents, you could just apply this thing, convert your system prompt, long system prompt to this thing, and just apply that. And it gives you a very clear footprint, blueprint for your AI agent to follow. So then, the question is, how do we measure success? And we have some benchmark results, of course. There are two popular benchmarks: Grade School Math, 8K, 8,000 questions, and Grade School Math Hard, where they scrambled the numbers, the results. So it's more difficult for AI agents to just memorize and predict. And this is the graph. The blue ones are when you apply braid, and the pink ones are the natural performance of these models. And of course, you cannot read it, but it starts with GPT 4.1, 4.1 Nano, and you know the price differences of these models, right? Like they're 20, 25 times cheaper. The Nano model with this approach can actually outperform the top model, which is like O1 here, or O1 Pro, which is brilliant because it's like 100 times cheaper than O1. If you give it a good reasoning structure, it actually performs almost as good as the top model. We also have another benchmark called Scale Multi-Challenge, because OpenAI, when they introduced GPT-5, they introduced this new, they tried it on this new benchmark, and you also can see the numbers now. This is practically GPT-5 high. Its performance is 57%. It's a very difficult benchmark. We went beyond GSM benchmarks and got into the territory of really difficult benchmarks. The actual performance is 57%. With Braid, you can improve that to 65%. But what is more intelligent is you can have a very cheap model, nano minimal, that doesn't even have any reasoning tokens, and it also gives you comparable performance for a fraction of the cost, because it's also generating way, way less tokens. And in fact, if you go here, we plotted the actual performance per dollar of all of these models. And you can see, I know it's very difficult to read, so I'm going to read it out. You can see GPT-5 Nano Medium is 33 times more efficient than GPT-5 High when it comes to price per dollar, or performance per dollar. 33 times more effective. For the same dollar, you get 33 times better performance, which is crazy. It's changing the game of AI. So now, you can spend half of it in your reasoning budget to make these systems way, way smarter. Okay, now, how does it compare to chain of thought? Yeah. I have 2 minutes. How does it compare to chain of thought? The methodology that every single AI agent uses, or AI system uses out there today. It's linear, it's prone to drift, and it's in ambiguous English. Whereas Braid is an executable blueprint for the same models of today to follow. And what if you built a specific model for this that understands mermaid charts and that executes them better, that can handle conditional logic better? So the future relies on what-if questions. We started with one. What if English isn't the best language to prompt these agents? And the next one is, what if you come up with the next what-if questions? Thank you so much.